Hey transportation enthusiasts, my name is Logan, and in this video we're going to talk about bridges. You're going to learn about how bridges are designed, the different stresses bridges must undergo, the different types, shapes, and structures used to make a bridge, as well as how bridges are tested, inspected, and some famous bridge failures. While watching the video, it'd be great if you could follow the steps, complete the tasks, and participate in our virtual bridge project. For the project, MnDOT is proposing a replacement for the Dinkytown Trail Bridge known as Northern Pacific Number 9 Bridge. You can see it on campus if you ever make it down there. The bridge is starting to fail and needs a replacement truss bridge. What we're going to ask you to do is watch the video, complete the task to design, build, and assess your own bridge at home using materials you already have, and be sure to share the results with us. Let's get started. So our first objective is to design a bridge, but before we can do that, we need to know how bridges are designed in the first place. To learn a little more, we have our guest speaker Brandon Day, who's a MnDOT bridge engineer, here to talk to us. They're all yours, Brandon.
So what do bridge engineers think about? We think about load paths, forces, connections, and stability, among other things. What's a load path? Well, we call the weights and forces a structure has to hold loads. Loads must travel through the structure until they find the support of the earth. Each part of the structure has to do its part. For this project, you won't have to think about load paths too much. In this picture, we see a load in the center of the slab. The load goes through the slab, which is gray, to the beams in orange, to the columns, to the footings, to the earth. Other loads must also have a load path. Wind can blow from the side where it pushes the walls to the beams, to the columns, to the footings, and down to the earth. There can also be water loads, earthquake loads, etc., etc. All of this has to be thought about. Let's talk about forces. Here we see compression. Things getting pushed together, squeezed, squashed, squished. Bridges see compression in the columns that hold up the middle of the deck. Here we see tension, pulling apart and stretching. We see tension in the cables of suspension bridges and cable stay bridges. When a beam bends, the top compresses and the bottom stretches out just a little bit. There is a line in the middle called the neutral axis, which stays exactly the same length. When the load gets to be too much, the beam will break. Either the tension makes the material stretch too far and it pulls apart, or the compression squishes it too much and it crumbles. We see torsion, this twisting, when the wind blows on the side of a bridge, or sometimes when a bridge is built in a weird shape. Below you see pictures of shear. For shear, think about what happens when the first tires of a truck get on a bridge, right at the very end of the bridge. Those tires push down on the deck and the beams, and it's like trying to slice a plane through them. Bridge engineers also think about connections. Connections will be super important to think about for your project. Most of your bridges will probably fail at their connections, so we'll think about how to make them strong. We also think about stability. See all the red arrows? They are pointing to cross members that help keep the girders stable. If the cross members weren't there, the girders might tip over. We want structures that are stable and don't tip over. Let's talk about the types of bridges. All of the bridges I work on are girder or beam bridges. Beams and girders are basically the same thing, but girders are made out of steel and beams are made out of concrete. Beam and girder bridges are the most common types of bridges because they are economical to build, meaning they can be built quickly and they cost less than other types of bridges. They just don't look as fancy. Let's look at some of the other types of bridges. Here we see what we call a flyover bridge near downtown Minneapolis. There is a steel bridge over the concrete bridge. Flyovers exist where many different roads come together. This is the Franklin Avenue Bridge in Minneapolis. Here, arches are doing all of the work to support traffic. This is the St. Croix Crossing Bridge near Stillwater. It is what we call a cable stay bridge. As traffic crosses the bridge, the cables are pulled, and the weight of the vehicles is transferred to the towers in the middle of the bridge. Supports in the middle of the bridge are known as piers. Supports at the ends are called abutments. You probably know what bridge this is. It is the Golden Gate Bridge in San Francisco. This is a suspension bridge. Many suspension bridges also have beams or trusses under the deck to help support the loads. The same is true for many cable stay bridges. Bridges are designed to be stronger than they need to be.
Watch them cables.
Let's have a look at this video.
Ooh.
Oh,
Wow.
look at that. Oh, Jesus. Look at what? Look at
Look at the dip.
Oh, yeah.
This bridge was designed for pedestrians.
Oh, keep honking, buddy.
Freaking honking.
Nobody wants on that bridge.
Look at that.
Oh, are you videoing?
Yeah. Holy cow, look at that.
I know it'll be a long time until you start driving, or at least it should be. But if you remember nothing else from today's presentation, let it be this. If your vehicle barely fits on the bridge probably wasn't designed for your vehicle.
Thank you, Brandon, for that wonderful insight. Now your task is to draw 2 rough sketches of bridges you would like to build. Be sure to choose your shape wisely, remembering what he said about compression and tension, torsion and twisting. Design away. Now that you have some sketches of bridges you'd like to build, let's move on to our second objective, which is to use principles of bridge design to create a model of a bridge. We're going to go back to Brandon, who's going to walk us through how we can do that. Take it away, Brandon.
Let's talk about how to build bridges out of stuff you have around the house. Maybe you have some Legos. If you have Legos, let's see how to best use them. Here's a beam, and we can do better than this beam. Let's think about what we learned about beams earlier. We see that picture of a beam in bending. There is tension in the bottom and compression in the top. Legos can compress with no problem, but tension will give you trouble because it will try to pull the joints apart. With Legos, shear will also give you trouble. Use your long pieces on the bottom. This will help resist tension. You can see the yellow pieces. Center the pieces on the joints. This will help you resist shear. The more beams you put on your bridge, the better. The deeper the beams are, the better. Make the deck out of whatever pieces you can stitch together. And when you're done, add rails to the side so you don't end up like this joker. Let's think about a beam bridge made out of cardboard. If we just use a flat piece of cardboard, we know that a can of soup will collapse it. It won't resist bending very much at all. We'll fold this to make it stronger. Squares and shapes with more than 4 sides can deform easily. Triangles hold their shape. That's what we want. So we take our piece of cardboard and draw lines splitting it into 4 equal areas. We fold it along the lines, and you can use a straight edge to help you keep the fold straight. Add some glue to the 4th side and fold it into a triangle. If you don't have glue, you can wrap it in tape. Use some clips or a book to keep it together while the glue dries. Now you have a nice strong shape that will resist bending. Make many of these and glue them side by side. Glue a piece of cardboard on top and you will have a strong bridge. For an even stronger bridge, you can add triangular beams in the gaps. This will also add stability. Now this next idea is the trickiest, but I think it looks the coolest. Let's think through an arch bridge made out of cardboard. In case you're wondering, the bridge in the picture is actually made out of cardboard. Now maybe you have a ton of popsicle sticks laying around. Let's look at how to build a truss bridge out of them. Take a look at the diagram and familiarize yourself with the parts. The bottom chord is in yellow. In blue we have the top chord. Red is the diagonals. And green we call the verticals. Like we saw earlier, triangles resist deformations well. It is the triangles that give trusses their strength. There's about 1 million different configurations for a truss. You can see some examples here. You can go online or you can just make one up, but you have to use triangles to make it. Like I've tried to emphasize, you should plan ahead. Draw your truss out. You can even trace the popsicle sticks on a piece of paper if you want. Think about your connections. For a popsicle stick truss bridge, it will almost certainly be the connections that fail first, not the sticks themselves. You'll need to think about stability too. All of those blue arrows are pointing to cross members that connect the top chords. This adds stability to the structure. Once you start loading it and the bridge begins to deform, each side truss will bend in or out if there is nothing preventing them from doing so. The same is true on the bottom, but you will have a deck on the bottom that will prevent this effect. Let's see what we can learn from these two pictures. They're pretty important. On the left, you see connections that will probably fail without much load. The connections on the right will survive a lot longer. The bridge on the left looks pretty skinny, and when the cross members on the top are added, those cross members might hang over the sides. You can cut those popsicle sticks with a good set of scissors so they don't hang over. The pieces that you cut off can often be strategically glued to connections to make them stronger. On the right, the bottom cord is wider because there are more popsicle sticks. This makes it stronger, but it also means that there is more surface area to glue popsicle sticks to for the deck. When you glue the popsicle sticks on for your deck, the diagonals might get in your way. Here again, one option would be to cut the popsicle sticks so that they fit. This is a bridge that doesn't have its deck on yet. Imagine if someone made one or two more bottom cords exactly like the ones you see, but used them as beams to go under the center of the deck, between the two bottom cords. It might be hard to visualize, but that blue line would be sitting on the floor and glued to the bottom of the deck, like an extra beam. Now I know what you're thinking. What if I don't have Legos, cardboard, or popsicle sticks? Well, you can try spaghetti noodles. It was reported that the spaghetti arch you are looking at here held about 570 pounds before it shattered. You can make a truss or an arch out of spaghetti, but I will show you how to make a beam, just to give you the idea. Recall that a beam in bending will compress at the top and stretch at the bottom. Now imagine if each level of the beam could slide relative to the other. That beam wouldn't be a very strong beam. The glue will prevent that sliding. Here I use a zip tie to keep the noodles lined up. You could use a rubber band or a clip or your hand. With the end of the noodles in place, I put a lot of glue in the other end. Then I squished the bundle back and forth a couple times to make sure each noodle got glued to the noodles next to it. I then zip tied the end I just glued and cleaned the extra off with a paper towel. I repeated the process at the middle and at the other end. After letting it dry for a while, I snipped the zip ties off. You can see that the noodles hold together nicely. I'll warn you though, in the places where the glue was, the noodles got a little bit brittle. That means it might fail with less load. A different kind of glue might work better. If you made an arch out of spaghetti, you would have to offset the noodles in the main arches, which is to say you wouldn't line them up like I did at the beginning of my beam. You would also have to come up with a good way to make connections to the deck, like you see in those red circles. And don't forget to add cross members on top for added stability. So I've shown you a few different options. You'll have to be creative. You'll have to plan ahead and think about your connections. Try to figure out the problems you might run into before you start, and figure out the solutions before you put anything together. Remember, measure twice, cut once. I want to thank you for your time, and I hope you come up with a great idea. Don't use anything that will get you in trouble if it breaks. Don't be like that kid.
I want to thank Brandon for his insights on making bridges using materials you have at home. Thank you for his time, sharing all those great ideas. And now we challenge you to build a bridge model using materials you have laying around your house. We don't need you to go out and spend money. Just use what you have laying around. It could be, as he showed you, Legos, cardboard, popsicle sticks, pasta noodles, toothpicks. You can hold it together with wood glue, hot glue, marshmallows. I've seen bridges made with gumdrops and toothpicks. Use whatever you have, be creative, and make a bridge. The parameters we want to stick with are, we're shooting for a truss bridge, so a bridge made with triangles. I want a deck on the bottom so that a vehicle can drive across. Make your bridge 20 to 25 inches long. Try to keep the mass of your bridge as light as possible. A lighter bridge means less materials. Remember what Brandon said. Don't make it out of something that if it breaks, you're going to get yourself in trouble. And everything he walked through was not instructions. Those were just examples. So be creative, make it on your own. And if you'd love to share your bridge when you're done, send some photos to ctsedu@umn.edu. I hope you've had a chance to build a bridge you can be proud of. So we can move on to our third objective, which is to strength test your bridge and see how much load it can carry before it fails. But first, let's hear from another engineer, Jim Archer of Bolton Menk, and he's going to talk to us about load testing bridges, how they inspect bridges, and some famous bridge failures. So now I'm going to pass it off to Jim.
All right, so bridges. Let's talk some bridges. Basically, Federal Highway institutes a bridge safety inspection program to monitor bridge health across the country. That program kind of stemmed from a couple famous bridge collapses, namely the 1967-ish collapse of the Silverdale Bridge, which was a wrought iron pin and hanger type structure, fracture critical, non-load path redundant, and they learned about bridge coupons and fatigue crack prone details from that structure. That kind of kicked off a bridge health monitoring initiative, if you will, that encourages us to take critical looks at structures around the country on a regular basis. So Federal Highway institutes that program, and we do a lot of bridge safety inspections for cities, municipalities, counties, and each state is left to their own devices on how they implement that program. Part of that program is load rating. Load rating bridges is effectively taking the capacity, the live load capacity, and dividing by the demand, the live load demand. So we're looking for ratios above 1, basically, and then bridges will be given a load rating factor, LRFR, that will determine basically either their capacity related to the design truck or a tonnage, depending on the bridge, so it'll be specific. You may see in rural settings, you'll see load posted signs for bridges, 9-ton bridge ahead, etc. That gives commercial vehicles warning that certain loads are prohibitive from crossing that bridge. You'll see other signs that may have different silhouettes of different trucks. That's just alluding to the different axle configuration for different commercial vehicles. So that's part of the bridge safety inspection program, is having current load ratings on those bridges. In the inspection program, some of the things that we're looking for are warning signs of bridge failure or different maintenance needs. The two basic failure mechanisms are shear. In a concrete structure, shear failure would be evidenced by diagonal cracks at the end points or the beam bearing locations, and then moment or positive moment failure would be evidenced by vertical cracks in the positive moment or the center, if you will, of the bridge. You'll see vertical cracking in a shear beam or even in a steel girder as well. So those are some common failure mechanisms. Things that we're looking for in the inspection. We have condition states. So for every element of a bridge, the superstructure, basically your beam or your girder system, your deck, the driving surface, your substructure, your piers and abutments, all those different components, the railing, any ornamental railing, guardrail, bridge approach panels, expansion joints, all of those elements get rated on a condition state basis. And just recently, we've gone to a 1 through 4, 1 being favorable or in good condition, 4 being basically failed. And that condition state basis kind of helps put everything in the same category. So different states around the country are comparing apples and apples. Similar to the condition states, we rate at a more granular basis for things such as paint systems. So a steel girder may be given a rating based on its condition, whether it has fatigue-prone details, cracking, if there's distortion or damage, and then the coating itself would be rated. So if there's any chipping or flaking, that would maybe bump it from condition state 1 to condition state 2. If there's some speckling or rust, that could put it in condition state 3. and once a certain percentage, more than half of the coating is missing or gone, you would end up in a condition state of 4 for that paint system. From there, we have the failures, or most of you will be building bridges out of timber. Things to look for in timber construction are in shear failure. You're going to be probably use some glue or tape or string, bonding elements together to laminate them or strengthen them. In the vertical construction industry, you have what's called LVLs, or laminated veneer lumber. So they'll go board, glue, board, and laminate a section together to get a deeper modulus, a stronger beam. So one of the failure mechanisms would be for that lamination to separate, and then your load is being carried by a smaller section of material. You can see that more at the bearing locations, the ends of the bridge itself. Things to be looking for failure in the center would be vertical cracks, splitting. Torsion of timber is possible given the different wood grains. For strength, you want to orient the grain of your wood vertically if possible. Trying to think of other timber operations. Not a lot of timber bridges left in Minnesota. I mean, I guess there are. Timber was pretty common in the 60s. But we've kind of gotten away from timber just because it's a less desirable material, maybe not as long lasting, and definitely less predictable in a lot of environments. Concrete and steel, a lot more predictable products, and so we've gravitated towards them. Although you'll still see timber bridges used on the system occasionally, timber railings are a nice way to incorporate an aesthetic feel in a lot of the bridges in rural Minnesota. So another example of a bridge collapse that lessons were learned in was the Tacoma Narrows Bridge in, I believe, Washington State. And that structure was a two-girder system cable suspension bridge. And the issue that arises on that structure's failure, good video, by the way, if you check that out online, the bridge was in a valley that was susceptible to high wind loads. And what they had was a deep girder section and only 2 girders. And what happened was it ended up being like a swing set. Wind would hit the bridge and it would swing to the side. And then wind would be pushing down on the bridge. It would swing back and it would expose both girders at the same time. And it just kind of gained momentum until the bridge actually collapsed due to lateral loads. So that would be one example of lessons learned in bridge design. The second, maybe more familiar, the 35W bridge. That's an example. Galloping Gertie would swing wildly in the wind, and everyone knew that the bridge had problems. So that was maybe an example of how steel can fail more plastically, so it deforms before it breaks. 35W is an example of how bridges might fail ductily, so rapid fracture. It went from existing to pretty much not existing very quickly. And so, again, lesson there, the diaphragms used in design and construction were under-designed. Although the bridge was in service for nearly 60 years, 50, 60 years, we learned that specific design of the diaphragms is very critical. And so these are the things, as we look into the bridge safety inspection program and manual, that bridge safety inspectors are looking for in the field, signs of failure, so that we can prevent bridge collapse.
Thanks to Jim for sharing his insights. Now on to your task. You need to test your bridge, but first make sure you take some pictures of it for us. Set your bridge up so it spans a gap, as you can see in the photo, and then test how much weight your bridge will hold before it fails. You can set the weight on top, as you see in the middle picture. You can suspend weight from it if you have a bucket, or you can just add weight however you can until your bridge fails. It'd be great if you could take some pictures of your bridge being tested and your bridge after testing. And again, send those to us at the email address on the screen, ctsedu@umn.edu. We can't wait to see what you came up with. Now that you've had a chance to design, build, and test your bridge, I got a few things for you to think about. How did you come up with your initial bridge design? Did you change your design as you built your bridge? If so, why? What made you change it? Did you use any geometric shapes while you built your bridge? And if so, which ones? Why'd you choose those? Would you make any changes to your design after you tested it? Did you encounter any surprises? And did you like this? Was this fun? Would you do it again? Maybe share it with a friend. Hope you learned something. Hope you enjoyed the video, and thanks for watching.